수학의 장점은 뭐냐면 우리 아시안들이 미국에서 잘하는 게 수학이거든요. 왜냐? 영어를 안 했어요. 영어에 약한 아시안들이 미국 가서 잘하는 게 수학입니다. 왜냐? 그것밖에 잘 못하고. Well, maybe it takes too much time to solve everything, so why don't you do just x1? x1만 풀면 될 것 같아요. 뭐 어쨌든 그럴 수 있다면 구해야지. So yes, in Kramer rule, to get x1, we exchange the first column with this one, right? By the way, I got this problem in the following link. So if you type this link, then you can, if you have a computer now, and type this link, then you can see the solution of this problem. By the way, you have to bring computer every class, right? Yeah. I think it is a good idea to turn on computer now. Because we will check this problem, check the answers for this problem with Excel as well. That's great. Okay, thank you. So here is perfect solution. Remove the link. I got this problem from this link. So use Cramer's rule to solve this one, and then I basically cut and paste this area. Okay, so this is a system subequation, and we transform this one as a matrix form. And then Cramer's rule says that x1, x2, x3, we call the first column as A1, second column A2, third column A3, and x1 is the ratio between the determinant and another determinant, where in which we just exchange the first column with v, and x2 we exchange the second column, x3 we exchange the third column. That's all. Yeah. Actually, there is an intuition for the. Before I explain the intuition of Cramer rule, let's use Excel to check the answer. Okay. We run. So we can write Excel Visual Basic. That is easier, but in this case, let's just use worksheet function. Okay, so it is A matrix, and the B matrix is this one. Okay, so this is A matrix and B matrix. We have A matrix and we have B matrix. Right? And then we want to get x1, x2, x3, so we can basically multiply this one and inverse matrix of this one, right? And the solution is, if we multiply inverse matrix of this one to this one, it is a 3 by 1 column. Then we check. We highlight 3 cells, and then we matrix multiplication, and then matrix inverse of this one, and then this one, right? And then Control Shift Enter. So this is the answer. Okay. Well, here it is written as a fraction, but yeah. So about minus 2.3 and 9 and 8. This is the answer. Do you remember this is Control Shift Enter? So let's check Cramer rule. First determinant. Okay. First check determinant of A. Well, determinant of A is M determinant, M determ. And then this one. The determinant is 6. And then we wanna calculate determinant of A1. Well, determinant of A1, then we have to define A1 matrix. For A1 matrix, we can change the first one. So A1 matrix is basically 1, 3, 4. Original matrix, and we change the very first column. Right, this is A1 matrix, right? So this is, let's change this one and so into the other color. And then, so basically from the original, this yellow matrix, I change the first one with this one. This is the this color. Okay. So this is A1 matrix. So determinants of A1 matrix is M determ. Right? And then we similarly calculate A2 matrix. A2 matrix is again this same now. We can change the second one. So this is A2 matrix. And then we calculate determinant. M determ. Right? And then A3 matrix. A3 matrix is again we copy, paste, and then instead of third column we plug this one. Right? So A3 is empty term. Right? Now x1, x2, x3 is the ratio between, so now we can get x1, x2, x3 is simply, right, a1 divided by a, right, this is the A2, this is S3, right? This is a Cramer rule. Okay, so the answer is this one divided by this one, and I click F4 quickly, and then and the answer of these two are exactly same. Isn't it fun, right? Yeah. M inverse. So if you want to calculate inverse matrix of this one, for example, then inverse matrix of this one, then you highlight 3 by 3 matrix and M inverse, and then control shift enter. This is inverse matrix. Here to calculate it, I have M multiplication, M inverse, and then I did 2 steps in one line here. Okay, so M inverse. Whenever you have a question, you can Google it. Excel inverse matrix, something like that, and the command M inverse will come up. Okay. It is usually fun, right? 여기 왜 컴퓨터 안 가지고 그래? 컴퓨터 없어? 같이 봐, 같이. 컴퓨터 안 가져온 사람들은 얘는 왜 컴퓨터 가지고 다니라고 그랬어? 얘는 왜 컴퓨터 안 가지고? 컴퓨터를 꾸준히 항상 가지고 다니시기 바랍니다. 여러분, 파이낸스 전문가, 여러분 파이낸스 경영과잖아. 이렇게 엑셀 전문가라고 사람들이 간주할 거야. 아, 파이낸스 경영과면 엑셀 선수겠네. 근데 인터뷰할 때 엑셀 하고 뭐 하는데 못한다 그러면 뭐지? 공부는 제대로 했나? 이런 생각. 네, 그래 엑셀 매트릭스 엘지브부터 가르쳐주는 이유가 있어요. 왜냐하면 엑셀 선수들도 엑셀만 잘 쓰지 수학을 못하거든. 그러니까 막상 엑셀 쓸 때 매트릭스 엘지브를 엑셀로 어떻게 하는지, 왜냐하면 매트릭스 엘지브를 모르기 때문에 엑셀로 매트릭스 엘지브를 할 줄 몰라. 근데 여러분이 사회에 나가서 갑자기 인버스 매트릭스 구하고 이런 사람들이 우아할 거라는 거지. 왜냐하면 그 사람들이 이걸 쓸 기회가 없었거든. 왜냐? 리니어 엘지브를 모르고 사회에서 쓸 거를 생각을 못하기 때문에. 그래서 이걸 외워주면 여러분은 비록 엑셀의 초보자라도 이런 것부터 배워서 이런 것부터 보여주면 갑자기 사람들이 전문가로 오해할 수가 있는 거지. 그런 오해는 좋은 거잖아. 그러지? 네, 그래서 막 이런 것부터 가르쳐주고 엑셀 비주얼 베이직부터 가르쳐주고 그러는 거예요. 왜 잘 안 되나? 왜 이해가 잘 안 돼? 이거 다시 한번 보여줄까요? 이거. So I'll show this again. Solution. So we highlight 3 cells. So I want to multiply inverse of this one and this one, right? I want to multiply inverse of this one and this one. So I highlight 3 columns, and then first matrix multiplication M inverse. Still highlight 3 by 3, and then select these three, and then Control Shift Enter. Right? 그래서 예, 질문이 있으면 나한테 물어봐요. Whenever you have question, ask me.
지금 처음부터 복습하고 있어요.
복습? 아, 예. So I assume you understood it. 예. 네? 이걸 또 코딩으로 하고 있네, 직접. 아주 좋아요. 네, 직접 해보고 있네.
인버스 함수
예.
이거를 C라는 바스켓을 생성한 다음에 거기 넣어주려고 하는 여기에다가 예를 들어서 C 는 하고서 여기에 넣어주고 싶은데 이렇게 하면 오리 뜨더라고요.
그 A를 그냥 이렇게 해도 돼. 이게 없으면 되지, 이게 없으면 되는 거 아니야.
아 그냥 이렇게 하면 돼요?
이렇게 하면 C에 되고, 그 다음에 여기에 C를 넣고, 여기 있는 C 하면 되겠지?
근데 이렇게 하면 범위가 지정이 안 되잖아요. 어디에 생성할지가 지정이 안 되잖아요.
아니, C라는 변수에 이게 들어가니까. 한번 해봐. 될 거예요. 그 다음에 는 C로 하고, 이건.
여기요?
그러니까 이거는 C가 되겠지. 이건 C만 써주면 되잖아, 이제. C라는 정보를 여기에 넣는 거 아니야.
여기에 그냥 이거
거기에 C. 그래도 돼요. 네, 이제 될 거야, 아마. 되네.
근데
그렇지?
여기에 C를 만들고 싶은데
여기에 C를 만들고 싶어?
그러면 C를 거기에 출력하면 되지. range G1부터 I3는
C. 이렇게 하면 되겠지. 해봐요. 네. 아주 좋아요. 여기는 엑셀 비주얼 베이직을 하고 있어, 벌써. 네, 바로 그런 적극적인 자세. 아주 마음에 들어요. 그렇죠? 그러니까 내가 이렇게 보여줘서 엑셀 비주얼 베이직으로 할 수 있겠지. 이것도 그대로 코딩하면 되잖아요. 그럼 이들의 막 이렇게 번잡하게 막 이렇게 할 필요도 없이 한 번에. Does it working? No, not working.
Okay, M mod, M inverse. There should be no blank. There should be no blank. Yeah, M inverse, and then F from A1. Yes, and then parentheses, and then comma. You need a comma, and then comma over here because you want to multiply inverse of this one. So comma. No, not blank. Comma this one. And then now you wanna, that's it. And then parentheses. And then, well, that doesn't need, but it is okay. So, close it, another, And then Control Shift Enter. Do you have an? Yes,
So you working? So now everything's fine. 힘들어. Let's go to our course web page. By the way, I also found very interesting another YouTube lecture, Essence of Linear Algebra. I highlight in yellow. You know, if you click this link, and if you go to this YouTube, basically it is another YouTube lecture about linear algebra, but now it is like intuitive explanation. In Khan Academy, it is like mechanical, like they deal with number, but in this YouTube link, those are all like they explain everything intuitively, right? Like geometrically, less relying on the mechanical mathematics. So if you have like question about the what determinant means intuitively, then you can check this one. So for example, let's this one, determinant. Okay, it is just a 10-minute. It's just a 10-minute
Hello again.
video and
So
it
moving
explains
forward, I'll be assuming
what
that you
is
have a visual
intuition
understanding of linear transformations and
Technically,
how they're
it's just
represented
10
with
minutes. Let's watch
matrices,
it
the way
together.
that I've been talking about in the last few videos. If you think about a couple of these linear transformations, you might notice how some of them seem to stretch space out, while others squish it on in. One
Yeah,
thing
so
that turns out to be
basically
pretty
linear
useful
algebra,
for
so
understanding one of
multiplying
these
matrix
transformations
full
is to
vector
measure
is like
exactly
changing
how
the
much
space.
it stretches or squishes things. More specifically, to measure the factor by which the area of a given region increases or decreases.
Yeah, so if you multiply
For
A
example,
matrix
look at
to
the
2
matrix
by
with
1
columns
matrix,
3, 0, and 0, 2. It scales I hat by a factor of 3 and scales j hat by a factor of 2.
yeah, something like
Now, if we focus our attention on the 1 by 1 square whose bottom sits on I hat and whose left side sits on j hat, after the transformation, this turns into a 2 by 3 rectangle.
that, right? So
Since this region
matrix
started out with area
multiplication
1
changing
and ended
space.
up with area 6, we can say the linear transformation has scaled its area by a factor of 6. Compare that to a shear, whose matrix has columns 1, 0 and 1, 1, meaning I hat stays in place and j hat moves over to 1, 1. That same unit square, determined by I hat and j hat, gets slanted and turned into a parallelogram. But the area of that parallelogram is still 1, since its base and height each continue to have length 1. So even though this transformation smushes things about, it seems to leave areas unchanged, at least in the case of that one unit square. Actually though, if you know how much the area of that one single unit square changes, it can tell you how the area of any possible region in space changes. For starters, notice that whatever happens to one square in the grid has to happen to any other square in the grid, no matter the size. This follows from the fact that grid lines remain parallel and evenly spaced. Then, any shape that's not a grid square can be approximated by grid squares pretty well, with arbitrarily good approximations if you use small enough grid squares. So, since the areas of all those tiny grid squares are being scaled by some single amount, the area of the blob as a whole will also be scaled by that same single amount. This very special scaling factor, the factor by which a linear transformation changes any area, is called the determinant of that transformation.
So determines if there is
I'll
a
show how to compute the determinant of a transformation using its matrix later on in this video, but understanding what it represents
So the 행렬식 determinant, the intuitional determinant is that if there is a area whose size is 1, the determinant means that if we multiply or matrix this one, then the determinant is like a scaling factor. When there is an area 1 by 1 matrix, if we multiply this one to a factor, then it changes the space, and that one size of this one segment becomes another size, and that is the size of that area is actually determined. So scaling factor, the changing size of a unit area. So in this case, if we so in this case, the determinant is 2, right? So this one minus this one. So the determinant of this minus 1, 1 minus 1 is 2. It means that if we multiply this matrix, so this matrix, if we multiply any factor within the space in this matrix, then we have a new space, and if you have a size area whose size is 1, after this transformation, the size of this area becomes 2. Right? So determines scaling factor.
presents is, trust me, much more important than the computation. For example, the determinant of a transformation would be 3 if that transformation increases the area of a region by a factor of 3. The determinant of a transformation would be 1/2 if it squishes down all areas by a factor of 1/2. And the determinant of a 2D transformation is 0 if it squishes all of space onto a line, or even onto a single point, since then the area of any region would become 0. That last example will prove to be pretty important. It means that checking if the determinant of a given matrix is 0 will give a way of computing whether or not the transformation associated with that matrix squishes everything into a smaller dimension. You'll see in the next few videos why this is even a useful thing to think about, but for now I just want to lay down all of the visual intuition, which in and of itself is a beautiful thing to think about. Okay, I need to confess that what I've said so far is not quite right. The full concept of the determinant allows for negative values. But what would the idea of scaling an area by a negative amount even mean? This has to do with the idea of orientation. For example, notice how this transformation gives the sensation of flipping space over. If you were thinking of 2D space as a sheet of paper, a transformation like that one seems to turn over that sheet onto the other
Then
side.
it becomes negative.
Any transformations that do this are said to invert the orientation of space. Another way to think about it is in terms of I hat and j hat. Notice that in their starting positions, j hat is to the left of I hat. If, after a transformation, j hat is now on the right of I hat, the orientation of space has been inverted. Whenever this happens, whenever the orientation of space is inverted, the determinant will be negative. The absolute value of the determinant, though, still tells you the factor by which areas have been scaled. For example, the matrix with columns 1, 1, and 2, negative 1 encodes a transformation that has determinant, I'll just tell you, negative 3. And what this means is that space gets flipped over and areas are scaled by a factor of 3. So why would this idea of a negative area scaling factor be a natural way to describe orientation flipping? Think about the series of transformations you get by slowly letting I hat get closer and closer to j hat. As I hat gets closer, all of the areas in space are getting squished more and more, meaning the determinant approaches 0.
Smaller and smaller.
Once I hat lines up perfectly with j hat, the determinant is 0. Then, if I hat continues the way that it was going, doesn't it kind of feel natural for the determinant to keep decreasing into the negative numbers? So that's the understanding of determinants in 2 dimensions. What do you think it should mean for 3 dimensions?
Well, now it is a bit complicated.
It also tells you how much a transformation scales things, but this time, it tells you how much volumes get scaled. Just as in 2 dimensions, where this is easiest to think about by focusing on one particular square with an area 1 and watching only what happens to it, in 3 dimensions, it helps to focus your attention on the specific 1 by 1 by 1 cube whose edges are resting on the basis vectors, I hat, j hat, and k hat. After the transformation, that cube might get warped into some kind of slanty cube. This shape, by the way, has the best name ever, parallelepiped, a name that's made even more delightful when your professor has a nice thick Russian accent. Since this cube starts out with a volume of 1, and the determinant gives the factor by which any volume is scaled, you can think of the determinant simply as being the volume of that parallelepiped that the cube turns into. A determinant of 0 would mean that all of space is squished onto something with 0 volume, meaning either a flat plane, a line, or, in the most extreme case, onto a single point. Those of you who watched Chapter 2 will recognize this as meaning that the columns of the matrix are linearly dependent. Can you see why? What about negative determinants? What should that mean for 3 dimensions? One way to describe orientation in 3D is with the right hand rule. Point the forefinger of your right hand in the direction of I hat, stick out your middle finger in the direction of j hat, and notice how when you point your thumb up, it's in the direction of k hat. If you can still do that after the transformation, orientation has not changed, and the determinant is positive. Otherwise, if after the transformation it only makes sense to do that with your left hand, orientation has been flipped, and the determinant is negative. So, if you haven't seen it before, you're probably wondering by now, how do you actually compute the determinant? For a 2 by 2 matrix with entries A, B, C, D, the formula is A times D minus B times C. Here's part of an intuition for where this formula comes from. Let's say that the terms B and C both happened to be 0. Then the term A tells you how much I hat is stretched in the x direction, and the term D tells you how much j hat is stretched in the y direction. So, since those other terms are 0, it should make sense that A times D gives the area of the rectangle that our favorite unit square turns into, kind of like the 3002 example from earlier. Even if only one of B or C are 0, you'll have a parallelogram with a base A and a height D, so the area should still be A times D. Loosely speaking, if both B and C are non-zero, then that B times C term tells you how much this parallelogram is stretched or squished in the diagonal direction. For those of you hungry for a more precise description of this B times C term, here's a helpful diagram if you'd like to pause and ponder. Now, if you feel like computing determinants by hand is something that you need to know, the only way to get it down is to just practice it with a few. There's really not that much I can say or animate that's going to drill in the computation. This is all triply true for 3-dimensional determinants. There is a formula, and if you feel like that's something you need to know, you should practice with a few matrices, or, go watch Sal Khan work through a few. Honestly, though, I don't think that those computations fall within the essence of linear algebra, but I definitely think that understanding what the determinant represents
Yeah.
falls within that essence.
Isn't it great? It's
Here's
very
kind of a fun question to think about before the next video. If you multiply two
So, I mean, this is great. I mean, it is. Have you ever wondered, by the way, in your life, why determinants look like that? This video exactly explains why determinants, formula for determinants should be look like that. Because it is the size of the area, it is scaling factor. Today, so yeah, intuition of eigen. Yeah. So determinant actually so. Wikipedia also has a very good explanation about determinant. It is determinant, and it explains that determinant is basically size, right? If we are interested in determinant, this one we can think about. It doesn't matter whether you regard the stack of two rows or stack of two columns. So basically, it is A, B, and C, D. So it is stack of two rows. So A, B generates this vector, and C, D generates this vector, and by generating a parallelogram, okay, determinants means the size of this area, or means that if there is in the original space, if there's a unit area, after transformation through this matrix, the unit area becomes size of this determinant. And then actually it proved it. Yeah, this is a fancy way of proving the area of this part is AD minus BC. It is a fancy way. In order to understand this, you have to know inner product, but determinant geometry. Right, so we are interested in size of this one, then we can calculate size of this and subtract this part. And we will get the size of this area. Now, once we understand the intuition of determinant, then we can understand the intuition of Kramer rule, right? Kramer rule is kind of mechanical formula. And maybe wonder where the formula comes from, where the Kramer rule comes from. Well, there is also geometric interpretation. Kramer rule geometric interpretation. So it is another Wikipedia. Kramer rule has a geometric interpretation that can be considered also proof or simply giving insight about its geometric nature. The geometric argument work in general and not only in the case of two equations with two unknown fields. Here, so we have an example, right? A11, so we have a system's equation. And then we can write the system's equation in this way. Right? X1, A11, A2, X2, A1 to A2 to A2, right? So from here to here, so first we can check the area of a parallelogram determined by two columns of this one, A11, A21, and then A1 to A22. And this is the determinant as we just learned. This black area is the determinant, right? Now because we multiply x1 and x2, basically we are stretching this one by the amount of x1 amount of this one, and then we stretch this one by x2 amount of this one. So S1, this one becomes this area, right? This area. Right? Not this area. So multiplying x1 and this x2 becomes basically this vector. It becomes this vector. Because we are adding this vector and this vector, and which is this. Okay. And then our target is B1 and B2, right? B1 and B2. Right. So anyway, determinant of system is this one. So in general, when there are most variable like this, therefore the area, okay, so first we are basically stretching this one. So the area, where is it? More variable is parallelepiped, so in the higher dimension. Anyway, the area of parallelogram determined by now this one. we stretch this one and this one and this one. We fix this part. And the area of this one is we can calculate the area of this one, right? And then the area of this one should be same to the area of this one. It doesn't matter because height is same, so we can move this one around here. The size doesn't matter, right? So basically, we are investing in B1, B2 equals X1, A1, A21 plus X2, A1 to A22. And then equating this equation, okay, so right? So if we B1, B2, so we are changing B1, B2, A1 to A2, then we are thinking about this determinant, and this determinant is basically tells you the size of this area, right? Size of this area. So B1, B2 is this one, A1, A2 is this one. So determinant of this vector and this vector, and the determinant is generally size of this area. What size of this area is basically equal to size of this area, right? Because the height is same, right? So size of this area is exactly same to size of this area is the same to size of this area. Therefore, this determinant and this determinant should be same, right? Well, by the way, the second determinant is we can put x1 outside. Put x1 outside, and we know this is this one, and this is this one. They are same. So, and this and this are same. So this and this is same, right? So we are interested in x1. So we divide each side with this determinant. So we have Cramer rule. Right? This is amazing. This is the intuition of Cramer. Interesting, isn't it? 뭐 질문 있어요? 이해했죠? 이건 직관적으로 이해하는 게 중요한 것 같아요. 열심히 안 받아 적어도 되는데 다 있잖아 유튜브에. 유튜브 키워드만 좋은 시대, 요즘까지 좋은 시대가 뭐냐면 다 받아 적을 필요가 없어. 키워드만 적어놓고 나중에 검색하면 되잖아. 이거 노트를 만들 때 카피 앤 페이스트만 하면 노트가 되잖아. 얼마나 좋은 시대예요. 그렇죠? 여러분 스스로 책도 쓸 수 있어요. 뭐 열심히 받아 적지 말고 키워드만 적어놓고 나중에 노트를 만들고 싶으면 카피 앤 페이스트. 이해했나요? 자, 이제 디터미넌트의 지오메트리도 이해하고 크레머로의 지오메트리도 이해했죠. 뭐 이러면 오늘은 충분한 것 같아요.